It's because Makrand's in.
Nice to be giving a talk in person after such a long time. Hi, so I'm broadly interested in complexity, quantum computing, and probability. And so far, most of my work has focused on query and communication complexity, and some parts of optimization, particularly improving lower bounds for size of linear and semi-definite programs, and discrepancy theory and stochastic processors. So, I mean, in this short talk, I will briefly talk about two problems, separating query and query complexity for quantum and classical, and about lower bounds for linear programs for solving the matching problem approximately. So what's communication complexity and query complexity about? Let me briefly introduce the model. And communication complexity is a very powerful tool to understand limitations of different kinds of algorithms. So abstractly, there are two parties, they are given inputs X and Y, and their goal is to compute some function of these inputs, f of x, y, and to minimize the communication simultaneously. So this is the standard model introduced by Andy Yao in the 70s, and there are many variations. The parties can send random messages, they can exchange qubits, they can allow for some error. But at its heart, this model is about understanding this fundamental question about how much information needs to be exchanged in order to compute whatever you're interested in. It's a very powerful tool to identify information bottlenecks in your computation, because here you sort of stripped away the issues of computational power, and it's purely information theoretic question now. This has had a lot of impact in many different areas in understanding limitations from information theory, distributed computing, streaming algorithms, and many others. So in this talk, I'll touch on query complexity mostly, which is a subfield of communication complexity. I personally think of it as a very simple communication model. Here, this is very useful for analyzing certain types of algorithms, and these are query algorithms. So here, the algorithm gets the input as a black box, and it can make queries to the input, and the black box gives the answer of the query. And again, the objective is to compute some function of the input and to minimize the number of queries simultaneously. There are two types of queries that are quite useful. The first is you can query bits of the input. You can choose them at random. So what this gives you is exactly a decision tree. You first query bit x1, depending on that bit, you choose another bit you query, and so on. And this can be randomized decision tree. The second types of query, you can query input bits in a quantum superposition. So, and the black box also gives you an answer in superposition. So you don't need to really understand what this means, but this type of query exactly captures what a quantum algorithm does. So it's quite useful to understand them. Again, this model, we have simplified a lot of things. We are not counting how much time it takes to process each query. So we are using the number of queries as a proxy for the running time of the algorithm. So the maximum running time of this any algorithm in this model can be at most n. But still, this is already quite difficult model. There are many non-trivial results here in this setting, especially useful for understanding quantum algorithms, because almost all quantum algorithms are sort of captured by this setting, and the number of queries serves as a very good proxy of running time for them. So one of the questions that I was really interested in was to understand quantum and classical query complexity and their separations, meaning that suppose you want to solve the same task with either a quantum algorithm or a classical randomized algorithm. So how many queries do they need to make to solve the same task? Of course, quantum algorithms are always at least as powerful, but they're also limited because they cannot access the answer in the same way. After a long line of work, starting from the work of Simon, Peter Shor, and recently due to Tal, the best separation for some problem was like constant versus n to the 2/3, meaning that there is some task which quantum algorithms can solve with just constant number of queries, but classically it needs like n to the 2/3 queries, where n is the input length. And we managed to show that the certain problem, that's called k-fold correlation, gives a constant versus almost linear separation. This is essentially the best you can hope for. In fact, this is the best separation you can hope for between these two quantities. And this was conjectured to be the optimal or the best possible separation by Ernst and minus. Let me also mention that in an independent work, Shestov, Storzenko, and Wu, they proved a similar separation for a related problem. And my favorite aspect of this result is actually the ideas that go into the proof, because it gives you sort of a nice distinguishing feature between quantum and classical algorithms. Sort of tells that quantum algorithms are very good at computing dense polynomial with a very few queries, but classical algorithms are sort of restricted because they can only compute sparse polynomial in some sense. And one can make this rigorous, and this is where some very nice ideas that are more common in discrepancy theory and optimization. We use them to prove this result. So this is the first result I was going to talk about, and the second result is about the size of linear programs. Suppose you want to solve a problem in computer science by writing down a linear program and feeding it to a solver. And one classic example of this was from the 80s, when there were some claims that there is a polynomial size linear program for the traveling salesman problem. Of course, these turned out to be false. Yannakakis refuted them and abstracted out the main idea that was being used in these claims. And that's the idea of extended formulation, which is a very powerful way to reduce the size of a linear program. You can think of it like that. Suppose you want to write down a linear program for the traveling salesman problem. Right? We expect that whatever program you write down will have exponentially many inequalities. But one way to reduce the size is to allow extra variable. This gives you the freedom to represent your original linear program in a higher dimensional space. What you want is the shadow or the projection of the higher dimensional object is the original polytope. Just from this picture, you can see that it can help reduce the size, because on top you have you need 5 inequalities to represent that polytope. At the bottom one is a hexagon, so you need 6 inequalities. But in and of course, if you can solve your problem in a high dimensional space, that's going to be much faster, and it will also give you the solution to your original problem. In higher dimensional, this idea, which is very simple, can help a lot. It can reduce the size exponentially in some cases. That's why it was a long-standing open problem since Yannakakis started this theory, to show that these are to understand whether these sorts of objects can be very powerful or not. In the last decade, there have been several breakthroughs, started from the work of Fiorini, Masarpo, Kutatiwari, Devu, Rothfuss, and Lira, and Storer. We know that for some NP hard problems, and even for matching problem, which we can solve in polynomial time, one needs exponential size linear programs and even semi-definite programs. Let me stress that these results, they're really unconditional. They don't rely on any unproven assumptions. So they impose like very strong limitations on these powerful models. And one of my results here was I showed that for the matching polytope, which is a very classic problem in computer science and combinatorial optimization, if you want to write down a linear program that gives you a 1 plus epsilon approximate solution, you need n choose 1 over epsilon inequalities. So it may not be very obvious why this number, but this bound is tight because there is a very simple linear program that doesn't even use extra variables, and it has the same size, and it gives you 1 plus epsilon approximation. And this holds for all values of epsilon, so it generalizes all the previous results. And of course, the connections to communication complexity and other things might not be clear. And this is a long line of work that I won't have time to talk about here. But this relies on ideas that were developed in communication complexity to understand what's called the lopsided disjointness problem, which is very commonly used in data structures. And those ideas can be adapted to this setting with some work. So let me end with some thoughts on looking forward. So, I mean, of course, there are some very interesting questions in these areas about understanding average case separations between quantum and classical query complexities, improving quantum communication lower bound by quantum information theory. I'm very interested in improving lower bounds for semi-definite programs for solving computer science problems. And of course, discrepancy theory. There are many beautiful questions that I've worked on. I don't have time to talk about that. I think I'll end with that. Thank you very much.
Makrand.